Okay, I'm plugged in. Thank you. Thanks, Yura and Radu, for organizing this. Yeah. First, I want to advertise. I see a few people who are involved in OJMO. Mark dragged me into this, and I'm very. This is one of the editorial activities that I'm probably the most proud of. It's open access, open source. You don't pay for open access. It's all free. And Michael Paus has done a great job of organizing this. And a few years ago, I used to say, it's not at a point where I would recommend younger researchers to contribute to, and I was trying to get the more senior people to contribute to this to get it some cachet. But I think we're there now, and I think it's a fully fledged, very high quality journal. And so please think of us when you've got your next submissions. Or next work. So I'm looking at just composite optimization, and as Mark showed, we're just trying to find points, critical points of this function, and maybe we want to avoid saddle points. And algorithms that you might apply to this, you could apply Newton's method. Newton's great, but it's not globally stable. It's expensive, and it's not sensitive to saddle points or even maxima. You can apply descent type methods. Those are robust and cheap. They can be made sensitive to saddle points, but they need smoothness of some sort somewhere sneaking in, and they tend to be slow. Projection type methods, those are my favorite approach when I can do it. These are robust, they're cheap, they're fast, and they can be engineered to avoid bad local minima. So that's the thing I'm going to show you. This is sort of work in progress. I'm trying to develop more sharp statements about that. But the problem with the projection type methods is that a global analysis for non-convex problems it's generally missing, I would say. So what's the test problem that's kind of guiding my intuition for this is this orbital tomography problem. The physicists shoot some beam into these molecules that are kind of laid down on some substrate. And what's cool here, so they generate this data that looks kind of like this. And what the data is, it's photon counts on spheres in the far field of this object. And we have a model from the object to the data, which is just basically the Fourier transform magnitude squared pointwise. And the problem with this is that we only get the Fourier transform on these spherical sheets, and it's very sparse data, and we need to reconstruct these three-dimensional objects. But from the physical standpoint, what's cool about this is they're actually observing electron probability density functionals, which when I was an undergraduate, you would have thought with the Heisenberg uncertainty principle would not be possible, but they're actually now observing electron wave functions. So now we apply our algorithms. Our first approach to this, I always start with cyclic projections. I formulate it as a feasibility problem, and I don't care which point I find. I just want to find one point that comes as close as possible to satisfying all the different constraints that we might bring into the problem. First of all, the data constraint has to match the data, and then other things that we know about the physics that we can bring in. And I'll say more about that later, but we apply our algorithm. It's a cyclic projection onto all of the constraint sets, m constraint sets. In this case, we have 5. And depending on where we start, we get different answers for this, and the physicists don't like this, but they like this. From the mathematical measure, I can prove local linear convergence for this algorithm, convergence of the iterates. And so I can prove, at least from these parts of the plots, that everything's happening the way it should, as I expect. It's not a global analysis, so I don't know how long it's going to take before I get into this region of local linear convergence. And you can see, well, from this run, if you just looked at the rates of convergence, you would see no qualitative difference from the mathematical measure of convergence of this to be able to distinguish which is good and which is bad. And if we say, we'll throw in a L0 penalty or something to regularize the problem, the physicists say, hands off, you're not allowed to touch our model. Okay, so I have to, but what the physicists do is they all right, they then go to a different algorithm, and they say, oh, FENOPS HIL works better. And often when they switch to a different algorithm, they're implicitly switching to some sort of regularization, which they don't recognize. But anyway, so the question is, can you just from this basic model, can we switch the algorithm and possibly avoid some local minima that the physicists don't like and hit the ones that they do like? So feasibility model. So I started with smooth, possibly. I mean, most people think of smooth optimization when they see just sums of functions. That could be something like this: minimizing the square distance to all of my constraint sets. And this is nice, it's differentiable, and we want to find the critical points of this. Well, and the problem of this, if we're just looking at two-set feasibility, here's one set, here's the other set, is that there are lots of local minima here. And maybe the true solution is this point here. There's an associated gap between the constraint sets there, and my alternating projections algorithm would put me on one of these points here. But I could get stuck in another region that takes me far away from this. So the idea for how to avoid getting caught in these local minima is actually to deregularize the problem, not to regularize the problem, and to destabilize the algorithm. So I'll explain. So to deregularize, I just go from my smooth distance function to the indicator function of the sets, okay? And so here, where I was looking for critical points, trying to avoid saddle points, here trying to find the critical points of this, which are the points of intersection of the sets, okay? I have a problem with that because in every problem that I'm dealing with with the physicists, their problems are not consistent. The models are good, but they don't ever fit reality, what you actually measure. So this causes trouble here. So instead of finding an intersection of the point, I'm just going to try to find fixed points of my fixed point operator. And so now here, it really is. When you change the algorithm, you're changing the fixed point set because you're changing the fixed point operator. In this context, well, you're just kind of hoping that that the fixed points of that operator make some sort of sense with respect to, trying to find some point that's nearest to most of the sets or something like this. Or maybe there's a preferred set that you want to stay closer to. So you can adjust that. So we're saying, but in this case, for cyclic projections here, all of the local minima for my unregularized problem, just minimizing the square distance, pretty much match up with my fixed points of my cyclic projection operator. So I haven't really gained anything here. So now I want to move away from cyclic projections, but here's kind of a hint. If you look at the difference between these two, this solution and this solution, and we're looking here at the gap. Now, what is the gap? When we have 5 sets, we're just looking at the length of the circuit we take through the sets, because we're always hitting these sets in the same order. And so the gap associated with this guy is larger than the gap associated with this guy. So that's in some sense a notion of quality. Another thing to notice here is that these gaps, there's size. When we're minimizing a square distance function, that's good. We want that distance to be small. But there's also information in the direction. This is a vector. And so we want to use all the information, not only the size of the gap, which is the value of the objective function, but the direction of the gap. Okay. So here's cyclic projections. Let's just look at the 2-set case. So I'm going to talk about some work I did with Heinz and Patrick. Boy, oh my God. I used to always say, man, that was like 10 years ago. And now I have to realize, now that was 20 years ago. So the fixed points of the cyclic projection operator are you can identify these with best approximation pairs between the sets. Now, if you go to Douglas-Ratchford, which is one of my favorite algorithms, then this guy doesn't have fixed points. And you'd think that's a bad thing, but that's actually the special sauce here. That's the key to being able to filter out bad local minima that you don't like, and hopefully catch good ones that you do like. But the thing about this one is, okay, it doesn't convert, it doesn't have fixed points, but it diverges to infinity in the direction of the gap. And that's sort of what this characterization shows you, that if you take the Douglas-Ratford operator and shift it by the gap vector, that is a non-empty set. Oops. And we can characterize it this way. So the thing is, for non-convex problems and inconsistent problems, you're going to go off in a direction of the gap. Now, if the problem's convex, you're going to keep going in that direction off to infinity. If you're non-convex, you're going to go out in that direction and then get pulled back into a region of attraction of perhaps another local minimum. So your search for this algorithm for non-convex problems is going to be bigger than the search you would take for just cyclic projections. So how would I kind of lasso in this good-bad property of Douglas-Ratford? I look at the relaxed Douglas-Ratford. It's the Douglas-Ratford, it's just a convex combination of the Douglas-Ratford operator and the projection onto the first set C1. The order of this is important, and it's important that I do the projection on the C1. That's the one that I first reflect across there. So what are the fixed points of this? With Anna Martens, I characterize the fixed points for the case of one convex set and a Prox regular set, and then with Anna Martens in 2019, we got the full non-convex characterization of the fixed point sets. So the fixed point set, now this is non-convex, so I'm restricting the fixed point sets to some neighborhood U, and it's sort of characterized by these. If you look at these are sort of shadow points of the fixed points of the relaxed Douglas-Ratford operator, and this is an inclusion here, but it's tight if this condition holds. So here the gap again is the distance between these two shadow points, or it's the direction of the difference between these two shadow points, and this sort of gives you an idea of not only the direction of best approximation pairs locally, but also the size of the well of attraction. The bigger the gap, the bigger the gap here, the more this point is going to move. And you can control that by this parameter lambda. The closer lambda is to 1, you're moving this, as this goes to 1, this is going off to infinity. So you have a control parameter now. You can push these points out of a well of attraction of maybe these two best approximation pairs, and then push yourself into a different domain of attraction. That's sort of the heuristic, and this is pretty much heuristic at this point. Okay, so the relaxed Douglas-Ratford algorithm looks like this, and the fixed points of this are monotone with respect to this parameter lambda. So you've got two parameters, lambda 1 is less than or equal to lambda 2, and we've got to assume that this is non-empty. Then the shadow of the fixed point set for the larger lambda value is a subset of the shadow of the fixed points for the smaller lambda value. And remember, the larger the lambda value is, the closer we're getting to Douglas-Ratford, the closer we're getting to an empty set for inconsistent problems. Okay, so that's the characterization of the relaxed Douglas-Ratford. And the analytical results, Mark was hoping that I would say more about this. I didn't plan to say anything about the analysis of this, but yes, we've given sufficient conditions. A key for this is actually we need to assume that the fixed points, this mapping in general is multi-valued, but we have to have that it's single-valued at its fixed points. Sounds like a reasonable assumption, but we've given sufficient conditions for when that holds. Depends on the regularity of the sets that we have here, and these The weakly convex certainly falls into this category, but we can deal with sets that have actually inside corners and things like that. So slightly more general. We've given sufficient conditions for this, what I call almost averagedness on neighborhoods of the fixed points. This is a generalization of firm non-expansiveness and things like this, but with a slight violation. That's one of the regularities we need. And then sufficient conditions for metric subregularity, which is stability of the fixed point mapping at its fixed points. This generalizes Kardika-Loyosovich, so if you're metrically subregular at your fixed points, you also have a Kardika-Loyosovich type property with some function that, you know, maybe you don't know exactly the parameters of that, but in any event, qualitatively you have it. So we get sufficient conditions. If the function characterizing the metric subregularity is linear, then you have linear convergence of this method. And we actually showed that it was actually linearly metrically subregular for a lot of cases that cover phase retrieval like this problem. One problem with this analysis is it only applies to 2 sets, and in our orbital tomography we have 5. So what do you do when you have more than 2 sets? There are 2 ways to go about this. You can do a product space formulation, which is you take all of your sets, you put it on a product space, and then you combine that product space of your constraint sets with the diagonal of the product space, and the diagonal being the space where all of the elements are equal. And then you just apply your favorite algorithm to 2 sets on the product space. That's one thing. That's equivalent to just averaging. In metric spaces, this is a really non-trivial thing to do because you don't have addition. And so this operation is not so easy. John Borwein and Matt Tam in 2015 looked at a cyclic, sequential version of this where you apply Douglas-Ratchford to sets C1, C0, then Douglas-Ratchford to set C1, C2, then and so forth, and you just keep moving up your chain, and then you cycle around. And they proved a lot of really nice results in the convex case. Matt Tam and Anna Martins and I in 2018 looked at then just replacing this with the relaxed Douglas-Ratchford algorithm. And the cool thing here is that you notice if lambda goes to 0 here, then the cyclic version of the relaxed Douglas-Ratchford collapses to cyclic projections. So you can view this as somehow like a convex relaxation between cyclic projections and cyclic Douglas-Ratchford. That's what that is. So but you still have this one parameter that you can tune and move around. So and now just recently with my student Tidan Din, we've characterized the fixed points of the cyclic relaxed Douglas-Ratchford algorithm in the non-convex case. So just non-empty closed subsets of a Euclidean space, and the fixed points have this complicated looking characterization, but it's actually a lot simpler than I thought it would be, because I mean, if you look at this is a mess. But Tilan found a really nice representation of this, and notice we're looking at, this is the shadow of these y points. This is y is in the reflection of x across its corresponding set Cj plus 1. And then we're looking at the shadow of that on the previous set Cj. And similarly for x, this is the shadow of xj plus 1, where xj plus 1 would be the cyclic Douglas-Ratchford operator at that one operator in the chain, the shadow of that on the set Cj plus 1. And these coefficients here, these sum to 1. So it's a convex combination of pairs of points as we're moving around. And the pairs of points are always these are points in the sets. So the fixed points are in some convex hull of the constraint sets that we have. And that's good news. And the other interesting thing is, and this is really cool because it confirms what physicists have been doing since the 70s. With Patrick and Heinz, we recognized one of the physicists' favorite algorithms, hybrid input-output, was actually Douglas-Ratchford. And the way they do it is they do 40 iterations of HIO, And of course, that doesn't have fixed points because it's Douglas-Ratchford for an inconsistent feasibility problem. And then they stop it, and then they do about 1 or 10 iterations of cyclic projections. And what this tells us is that you run the cyclic Douglas-Ratchford algorithm to a fixed point, say, and then if you just look at the shadow of those fixed points constrained to some neighborhood, you're within an epsilon ball of the fixed points of the cyclic projection operator. So what the physicists have been doing for decades, it makes a lot of sense, because this is a bit more interpretable than that. So that's, the analytical results for this, 5 minutes. The analytical results for this, we've characterized the fixed points, I just showed you that. And then sufficient conditions for, we also need that this is single valued at its fixed points. We've proved almost averageness for, with arbitrarily small violation of that. Metric subregularity is still an assumption, but where we're going with that is I think we're going to use some characterization like semi-algebraicity to generically characterize some sort of metric subregularity property holding. So then this gives us sufficient conditions for local linear convergence, which we observe for this algorithm, in fact. And the issues here are, though, that when we play with this parameter lambda going from 0 to 1, 1 being the limit to cyclic Douglas-Ratchford, we lose fixed points, yes, but then we go to orbits. So we get weak convergence somehow. And these orbits, the shadows of the orbits, are tending to look distressingly similar to just the fixed points of the cyclic projections mapping. But anyway, that's where we are so far. We're not sure whether this is strictly smaller than the fixed point set of cyclic projections, but I think we can cook up some examples. So just to show you back to the orbital tomography problem, again, these are the sets that we're dealing with. This is the data set. This is the Fourier mapping here, the amplitude of the Fourier transform. This is what's measured. The payoff here is that the physicists were taking 50 measurements. Every measurement took them about a half a day, and we showed them that they could get away with just 4 measurements. So they can save a half a week to a week of lab time by using these algorithms. And then we put in symmetry constraints, sparsity constraint here, and support constraints. Except for the sparsity constraint, these are all convex constraints. This one's easy to deal with. And so this is the feasibility problem we're solving. And so this is all just phenomenological now, the empirical evidence. So the CDR lambda is in blue. We've taken a lambda parameter of 0.3. Of course, this is all trial and error, hunt and peck. And you see generally, CDR lambda never gets caught at the fixed points of the CP with this gap value. These are the gap values. And you see a general tendency towards smaller gaps, but none of this is yet proven. It's just giving me encouragement to keep hacking away at this. And so these are the references related. I meant to put, there's one more reference that got me thinking about this algorithm. Again, was a joint work with Mark and Shoham, where we just did a benchmark comparing all different kinds of algorithms, and this one just consistently beat every algorithm that we tried in all of our benchmarks. So that's why I kept going back, wanted to go back to this. But anyway, these are the main results. So thanks.
Thank you very much.